So in this lecture, we're going to talk about the SN diagram. As we mentioned last time, we have in fatigue assessment, we need two separate diagrams. The very first diagram that we need to know if my structure was going to fail or not. And for this, we had what we call the Goodman theorem, Goodman theory. Okay. So this was the Goodman theory, mainly Goodman. I'll sometimes use uh, the Gerber theory as well, but this is the most typical one. And that basically tells us if bigger than one is infinite life, equal to one, finite infinite life. Less than one is finite life. And note that this fatigue factor of safety does not represent failure. Okay, it only represents if I have enough life for the structure. Now, how do I know if I have enough life? I need to go what we call the SN diagram. In the typical sense, the SN diagram will look something like this. And the SN diagram, the N represents life cycles. Okay? Yeah, you can pause the video and take a snapshot of this if you want to. These are number of life cycles. And on this axis right here, okay, this axis, we have alternate stresses, okay, SA. Or also we call it sometimes fatigue strength. So if I have a loading system, right, in that loading system, I want to find my SA, what I will do is the load actually goes here. It is the Goodman stress. That's the one that we actually look for. So the Goodman stress is given by the following equation. So Goodman stress, equivalent stress, okay? And this applies to both, applies to brittle materials and ductile materials together, SM, SUT. Okay, this stress right here is the equivalent stress at fully reversed stress. Okay, and this stress is what actually was going to go in this plot here. And the way it works is you have a plot that looks something like this because it comes with a bunch of test data and we can curve fit it to look as follows. And what you have is this particular point is the point where you have low cycle fatigue. This is a big research area. Also, high cycle fatigue is a lot more mature than the low cycle fatigue. And what we do is your plot is coming from a point right here, ultimate tensile. And then you have a point right here, what we're going to call it F multiplied by SUT. And what is that factor F? We will talk about that in the next couple of slides. Just hold on your thought there. And then you come to this point somewhere close to 10 to the 6 typically. If you have a nice knee, okay, we call it a knee because you can see that it actually goes here and it just keeps on going to infinite, okay? It's a straight line. So this is what we call the endurance limit. This is the endurance limit. Okay. Okay, so that's called the endurance limit. And the way this really works is you will check this Goodman stress that you get from this equation right here. You would take that stress and then you will find where it is. If the stress is right here, let's say that is my Goodman stress number 1, let's say, right? And you can see that the stress does not intersect this curve at all. There's no intersection. That means that I actually have infinite life. Okay. Now if my stress was over here, let's say, as equivalent to, then what you can see is that I do intersect the curve, and that intersection will give me life cycles. See? And that will say this is how many cycles I have left of my structure. Now, I can also do the other way around. I can say, I could go ahead and say, what if I wanted to design something for 10 to the 5 cycles? I would just go up here, right? And then from here, I can go all the way up here and then say, oh, this is a value of sigma equivalent, let's say 3. I would take this stress and place it right here. And now I can solve for the diameter or the material, anything I need from these two guys right here, right? Here I can design, I can change the dimensions, I can change the material to fulfill a certain life pattern. Okay, so this is a typical diagram for a ferrous material. This is mainly ferrous. Ferrous, it means that it's iron base, has some iron. And that's how this plots actually look like. In the case of aluminum, as for an example, many of these actually don't have, this is a non-ferrous materials don't have endurance limit. So what do we do with non-ferrous materials? Well, in the non-ferrous materials, typically somewhere between these two, we will take a value and we will set that value. Instead of using a SE, we will have what we call SF. Okay, so it's a fatigue limit. This is the fatigue limit. Okay, and the fatigue limit is for non-ferrous materials. As for an example, aluminum is a very good example for that. Okay, so you can have a you can possibly have a case that actually looks something like this. If I can draw this, sorry. Okay, this is life left of the structure. This is fully reverse alternate, and you can have a structure that actually has a knee. If it has a knee, it will look something like this. And we can draw this a straight line. And then we can go from here in a straight line from here to there. Okay? This is very typical for this. Now, what I should also tell you is this is the typical approach, but many authors, what they will do is they will just draw a straight line from here to here, and that would be a very conservative approach. Okay? This is conservative. Why is it conservative? Look at this. Let's consider this case. Let's suppose I have a stress, equivalent stress that would come here. And this stress, if I come over here, you can immediately see I'm going to have less cycles. You see, let's call this N1. For the same stress, for the typical curve, I can call it N2. And you can see that N1 will be less than N2, so we are designing for less life. Okay. The other case is also true. What happens if I had a case where in which, let me delete this. You can pause the video and you can draw these lines. Let's do the other way around. Let's suppose what I want to do now is I want to actually apply for a certain end life, right? And I go all the way up, right? And what you can see is for the conservative, I am going to get a lower stress, call this sigma 1, than if I use the traditional approach where I get S equivalent, call it sigma 2. And you can see that S sigma 1 will be less than S equivalent sigma 2. And please don't confuse this one Mises. This is the equivalent stress from your failure theory, actually. Okay, so when you look at this type of equation, you can see that regardless if you're doing this or you're doing this, this is what it means to be conservative. Okay, now a typical SNDiagram has a knee, as I just mentioned, and A nicer diagram may look something like this, in where you want to find your fatigue strength, and just know that this fatigue strength is actually from your Goodman theory. Okay, that's what it is. This is Goodman theory. Okay, so, and then this is a log scale. So this is a plot log. Okay, so the plot here is actually given by, this curve is given by this equation. And you can immediately see that I'm going to have two separate equations, right? Because slopes are different. So you can say in this segment, this you're going to have a different slope than the one that you have here. But we'll talk about that later. Now, for this f, how would I calculate this f? Well, there are many cases. So first of all, if you're working for the case of this is less than 70 KSI, right? Then if it's less than 70 KSI, you will take F equal to 0.9. If your SUT is bigger than or equal than 200 KSI, then you take F equal to 0.75. Otherwise, you can use these equations. Just note that this equation is in megapascals. This equation is in KSI. They're both equivalent to each other, and all depends on the equation that you want to use, the units that you want to use and you're working in. Okay, so you have to know that these values in here, okay, they have to be consistent when you plug them there. Okay, so let's move on here now. So how do I find the endurance limit? When I'm going to find the endurance limit, now the endurance limit is actually going to equal to a K infinite. We will talk about this in a minute. That's multiplied by a prime. Now we can also have, in the case you want to have a stress limit, okay, I call it Kn, Sn prime. Okay, this is for mainly for non-ferrous materials. This is for ferrous materials. Okay, ferrous materials have a nice knee. These don't have a knee. Okay, so what are these SE prime? Your textbook gives you some of these, but I like to use the following. You may want to take a good note of this, but these are the ones I would like for you to use for your homework. When n is equal to 10 to the 6, these are the values that you're going to use for SE prime. There are two cases. First case is 0.5 SUT. This would be good if your SUT is less than 200 KSI, okay, or 1400 megapascals. And this is 100 KSI if this is SUT is actually bigger or equal than 200 KSI. Okay, this is for steels. For most irons, we can also have the knee, and you can see that for ferrous materials, typically the knee happens at 10 to the 6. Remember, the knee, I'm talking about this knee, this value right here. You can see that happens at 10 to the 6. You see, I'm talking about this value. But this value here is a reduced value. Okay, but so to find the reduced value, I will tell you where the values come from, but first you need to find this default value, this one right here. And that default value will depend on the type of material that you're using. So if it's most irons, and this will be 0.4 times SUT. If your SUT is actually less than 60 KSI, we will use 24 KSI if we are working with SUT bigger or equal than 60 KSI. Okay, Um, so this is for these cases. Now, if we are working for aluminum, aluminum is a typical material where your N is actually at 5, 10 to the 8. So this is, we're going to use in this case SN. Why we're going to use SN? Because we don't have a knee. I like to make this distinction. There are books that don't make the distinction. The book that call this F, I like to call it N. Okay, so it's F is 0.4 times SUT. For SUT actually less than 48 KSI, and 19 KSI if your SUT is bigger or equal than 48 KSI. Okay, so I think this kind of gives you a very good idea on the value that you will use, that we'll use in this course. Okay, now let's start here and let's start working our way around what are these values. I call this whole value system K infinite. Okay, now this loading factor, we already applied this loading factor to the actual stresses. So we do not use, so we will not use, because we applied this to the stresses. If you remember from the last lecture, you remember your sigma A was divided by KLA, right? And if you remember, your sigma B was divided by sigma LB, and your tau XZ was divided by KLS, all these at only for alternate stresses. Right? If you remember that, we did that last time. So since we already applied it here, there's no need to double dip again. Okay, there's no need to apply it again. So the factors that we are interested now to find are these other factors that were not included originally. Okay, so this is the endurance limit. This is what we find from testing. This is the correction. This is the correction so we can reduce it. And basically what happens is when we do your testing, your test specimen is never the same to the original specimen. So people, we as engineers are perfect in doing that. We like to say, can I use something that I know and keep using it and modify what I already know with something that, can I use something that I already know and modify it to use it for something I do want to use, right? That I don't know. So we do that all the time, and we find factors, different factors. This is one way to do it, and it's a very typical way to do it, very systematic way to do it. I love the way your textbook does it. So we're just going to work our way through these equations one at a time. First one is the surface factor. The surface factor is very easy. This is exponent B. This is factor A and A. This is going to depend on if you are working in KSI or PSI. So it all depends. If it is a ground finish, it's a machine cold drawn, is hot rolled, or as forged. If it's machine polished, if it says polished, then your Ka actually is equal to 1.0. Okay. Otherwise, you just apply these factors here to the A. So you will your new factor A would be A times SUT times B. You know this. These two will come from this table. Okay. So this is your first factor. Your second factor would be the size factor, and your size factor, mainly if you're working in bending and torsion, is when we really like to use the size factor. Axial load really doesn't affect much. We can take that equal to 1. But you can calculate this by hand, and in your MATLAB code, you just calculate this by hand and you input these values. Now, this is all given in round bars, as you can see. And the question is, what happens? Oh, just remember, this is millimeters, and these equations are for inches. So the question is, how do we do if we had different shapes? Well, your book does provide that approximation. So your book says, well, the areas that the diameters that you will use for data analysis, the D's that would go in here, they are actually given by these equations, okay? So this is the D that you want to, this is the D that you would like to use. This is equivalent D's that you want to use in your analysis, okay? So then the next factor is your temperature factor, okay? Your temperature factor, let me move this from here. Your temperature factor is very easy. If you're working in Fahrenheit, you use this equation. Working in temperature, you use this equation. And I know that this can go above this. So the way I like to do is I don't want this factor never to be above 1. So if it does go above 1, I would default this factor to 1. Okay, you always want to make sure it stays to 1. It can be less than 1. Most of these factors that we did, I should warn you, they are actually equal. So any factor is actually equal or less than 1. That should be the criteria you keep in mind. Okay, so you know what your temperature is, plug in the numbers, and that's the value that you get. Okay. Now, your reliability factor comes from a reliability. Typically, what we are interested in a 99% reliability. Now, you can make the structure as reliable you would like to have it. And if you want something very, very reliable, you're going to pay a big money for that. You're going to pay lots of money for that. And we don't like that. So unless it's a very specific part, then you really care for that precision or reliability, that you want to make sure that it's going to last you that long and you can rely on that. The probability of failure is very, 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 very small. Then in that case, well, then we have no other choice, right? So you choose the percentage probability, and that will give you what your probability factor is. And you can, yes, it's not correct to interpolate, but if you wanted to, you could do a simple linear interpolation here. Your MATLAB code actually gives you these values for different reliability factors. Okay. Then you also have miscellaneous effects. These miscellaneous effects are because of residual stresses, cold working, maybe you have hardening. And we didn't even talk about torsion fatigue. Torsion is a big issue, especially in aerospace structures, in marine structures, and cars, and trucks. And so this value right here, when you design this, you want to put a corrosion. If you're working with moisture, you may want to put a value maybe around 0.8. Surface conditioning, maybe these two actually electroplating or spraying. Sometimes we spray your panels so they don't get corroded, but that actually affects you pay a price, you pay a penalty for fatigue. If you get any other, maybe going high speed, then maybe you have a speeding, include a speeding criteria there, or et cetera, et cetera, et cetera. So there are many things that could enter in this miscellaneous effect. So at the end of the day, you have this K infinite, and this K infinite will be the multiplication of all these factors that we just talked about. Okay? You multiply them. This is a multiplication. So once you have that factor, then we have our SC, right? SC prime, or we have our SN prime. Then you will go ahead and say, okay, now I can calculate my SN, where it says K infinite, which I just calculated, multiplied by my K infinite SN prime, or SE equal to K infinite SE prime, okay? So in this particular course, the way I'm going to focus my attention is mainly with the problems in which we have a perfect knee, but you are responsible to understand this as well, both for quizzes and your exams. Now, Another thing that we do the assessment, right? We have two separate diagrams, and we need to know how to handle them. So let's see. Let me give you one example of that. Okay, this is an example. Actually, your MATLAB gives you these two plots, and you can see that this is the SN curve, SN diagram for these plots. So just to show you how this works, just illustration purposes, how the both plots actually are related. Now, as you can see, this is the endurance limit, right? This endurance limit, this line is actually belongs to this line over here. And any stress that belongs underneath this, right, here, is the same stress that will actually belong underneath this line. Okay, as we talked about last time, anything inside this curve, right, inside here is infinite life. So anything below this is also infinite life. It kind of makes sense, right? So as we go, let's say a point is over here, and you can see my point is actually here. It says actually it's not acceptable, okay? But if it was acceptable, your fatigue stress is 33.23, and that stress is actually going to give you here, and you can see this is your traditional curve, this is your traditional curve, this is the conservative curve, and you can see how the values give you, right? This gives you a lower life. You can see the life that I get versus the life I get if I have the traditional approach. We are talking a significant amount of difference of life. This is about 1400, and this life is roughly 12,000. So you can see the significant difference between the life cycle between one another. This is huge. So that's why we like to actually use this curve, and your MATLAB code actually does all these plots for you. Anything above this line, so if you have a value here, that value will actually correspond to a value above this endurance limit. It will be above this line because everything here is finite life. Okay, that's how we actually use this curve. This is how it actually works. So next thing we're going to do is we will do a couple of examples to bring all this together to see if we can understand how it's going.